Welcome back. So, we've talked a lot about simple models, but let's be real, the world isn't a straight line. It's full of twists and turns, and our data usually is too. So the big question is, how do we get our models to capture those complex, real-world patterns? Well, today, we're going to do exactly that. We're going to learn how to bend the line with something called polynomial regression in scikit-learn.
All right, here's the game plan. We're going to start with the basics, the power of straight lines with linear regression. Then we'll see exactly where that approach starts to break down. From there, we'll build our way up to creating a much more flexible, curved model, figure out if it's any good, and finally, talk about the really important trade-offs that come with all this new power.
So, to get us started, let's imagine an ice cream truck owner named Jeff. Now, Jeff knows his business. He knows that when the temperature goes up, his sales usually go up too. But he wants to get smarter about it. He wants to use his data to predict exactly how much ice cream he's going to need on any given day.
Jeff's first tool, his go-to, is linear regression. It's really the foundation of supervised learning, and it's perfect for this kind of problem, finding a simple straight-line relationship between one thing, our input like temperature, and another thing, our continuous output like sales revenue. The whole goal of this model is to find the perfect equation for that best fit line. It's trying to learn the ideal values for m, that's the slope, how steep the line is, and c, which is the intercept, or where the line starts. These two values, m and c, are what we call the model's parameters.
And this right here, this is basically the standard playbook for scikit-learn. It's a beautiful, simple workflow. First, you get your data ready. Then you create a model object. You train it on your data using the .fit method. And once that's done, you can use .predict to forecast sales for a brand new temperature. It's simple, but it's really powerful.
But Jeff keeps collecting data, and as he does, he starts to notice something. A little weird. His trusty model works great on most days, but it totally falls apart when things get a little extreme.
Think about it. What happens on those really, really hot days? People don't just keep buying more ice cream. No way. They stay inside where there's air conditioning. So his sales actually start to drop. A straight line can't do that. They can only go up or go down forever. It has no way to capture this real-world pattern of peak and then drop.
And this problem has a name. It's called underfitting. Jeff's linear model is just too simple to understand the true story in the data. It's making a huge, oversimplified assumption that more heat always equals more sales. We call this high bias, and it's a huge signal that we need a more flexible, more sophisticated model. So, to solve Jeff's problem, we've got to upgrade our thinking. We need to stop trying to find the best fit line and start looking for the best fit curve.
And this is the fundamental difference right here. Look at the equation for polynomial regression. We've added a new term, an x squared. Just by adding that one piece, we give our model the ability to bend, to create a curve. That's what gives it the flexibility to follow a more complex pattern in the data. Now here's the really clever part. We don't actually need a totally new, complicated model to do this. We use a trick, a kind of data judo called feature engineering. We take our one input feature, temperature, and we literally create a second feature out of it, temperature squared. It's that simple.
Okay, so theory is great, but how do we actually pull this off in scikit-learn? Well, it turns out to be a surprisingly straightforward two-step dance.
Step 1 involves this special tool from scikit-learn's pre-processing library. It's called polynomial features, and its entire job, its whole purpose in life, is to take our original data and automatically create those new powered-up features for us. It does all the math so we don't have to. And you can see that transformation right here in this table. We start with just a single column of temperatures, right? We feed that into polynomial features with a degree of 2, and what comes out is this new table. It has a column for the bias, our original temperature column, and a brand new column with the temperature squared. So the workflow looks like this. You transform your features into polynomial features, and then, and this is the really cool part, you train the exact same linear regression model we used before. But this time, you're training it on this new, richer data set. The model just sees temperature and temperature squared as two totally separate inputs, and by finding the right weights for both, it learns how to draw a curve. Okay, so we've gone and built this new, more complex model. But in data science, you can never just assume it's better. You have to prove it. We need a concrete way to measure performance and see if we've actually made an improvement. One of the most common ways to do that for regression is the metric called R-squared. The easiest way to think about it is like a score, from 0 to 1. It basically tells you what percentage of the change in sales can be explained by the change in temperature according to our model. The closer you get to 1, the better your model is at explaining the data.
And when we put our two models head-to-head, well, the results are pretty darn clear. The original straight-line model might get an R² of, say, 0.65. Not terrible, but our new polynomial model, it scores a 0.98. I mean, that's quantitative proof right there that our curve is a much, much better fit for Jeff's real-world sales data.
But numbers only tell you so much. For me, the real aha moment comes when you actually visualize it. When we plot both models on the same graph as the data points, you can just see it instantly. You see the straight line just slicing through the data, totally missing the point. And then you see our new curve, just elegantly weaving through the points, perfectly capturing that peak and that drop in sales.
Now, our new model is looking fantastic, but this newfound power to create complex curves comes with, well, it comes with a word of caution. It introduces a critical idea that every single data scientist has to master, and that's the bias-variance trade-off.
Remember that degree we chose for our polynomial? That's what's known as a hyperparameter. Now, this is different from a parameter like the slope, which the model learns from the data. A hyperparameter is a setting that we, the data scientists, choose before training even begins. Think of it like a knob or a dial that we get to tune to control how complex our model can be.
And tuning that knob is a delicate balancing act. If we turn it too low, say degree 1, we get our original problem, a model that's too simple and underfits. But if we crank it way too high, to like degree 10, the model becomes too powerful. It gets so flexible that it will wiggle and bend to hit every single data point perfectly. It ends up memorizing the random noise in the data, not the true pattern. And that's called overfitting. So the real goal is to find that Goldilocks spot, that sweet spot right in the middle. We want a model that can generalize well, meaning it performs accurately on new data it has never seen before, not just the data we use to train it. And this, by the way, is why a non-negotiable best practice is to always split your data into a training set and a testing set so you can check if your model has just memorized the answers. And that question right there opens up a whole new world of things like hyperparameter tuning and cross-validation. These are the essential skills you'll need to find the perfect model complexity for your own projects. Mastering this balance is really your next big step on the journey to building models that are not just accurate, but truly robust and predictive. And now, you know how to go beyond straight lines to capture the real curves in your data.
Like and subscribe for SimplfyTech, explaining one concept at a time, simplifying the technology and AI.